So section 12.4, the last section of the last chapter of the pure A-level course, and this is just saying everything in mechanics that we know about with one-dimensional vectors and two-dimensional vectors is still true for three-dimensional vectors. Those vector equations, the vectors in those things are vectors. So if those are vectors in 3 dimensions instead of 2 dimensions, the equations still work. So for example, if I've got F1, F2 and F3 and I want to find the resultant force, one way to do that is to think of F1, F2 and F3, F1, F2, F3, and the resultant force is F1 plus F2 plus F3, and there is my resultant force. Okay, so that's true in 2 dimensions, it's still true in 3 dimensions. So if we take those 3 vectors that they give us in example 13 on page 347 and we add them together, it gives us the resultant force. If we want to find the acceleration, we have the formula F equals ma. So we take the resultant force, that F in F equals ma is the resultant force. So we take the resultant force and we divide it by m. In the case of vectors, that means timesing it by 1 over m. Or timesing each of the components by 1 over m. Again, sorry, it's a very windy day. I've got a rattly window in this room. Apologies if you can hear that one. Find the magnitude of the acceleration. Well, magnitude of the acceleration means the magnitude of the acceleration vector. So when we find acceleration here, we're going to get a 3-dimensional vector. Find the magnitude of it by the technique that we know for finding magnitudes of vectors, right? And then find the distance travelled by the particle in the first 6 seconds of its motion. Well, in order to do that one, what do we know? We know that s equals ut plus 1/2 at squared. We know that these things here are vectors and that s is the vector for displacement, right? So we could use the initial velocity as a vector, the acceleration as a vector, and put all this stuff in as vectors. T is 6 because it's asking about the first 6 seconds of the motion. But we can actually shortcut that a little. So I'm saying that because the whole idea here is that everything in the mechanics works in 3 dimensions, works with vectors as well as with one-dimensional vectors, like whether with plus and minus numbers. But actually we can shortcut this a little bit because we've got u, v, a, s and t. U is the initial velocity, and it tells us that it starts at rest. I don't care about the final velocity. The magnitude of the acceleration is all we want. If we don't want to know the displacement, but we just want to know the distance it's moved, then the magnitude of the acceleration will work. So from part C, I can put that in as 140 on square root 140, sorry, for the example that we're using. And time, we do care about time. Time is 6, and s is the thing we're trying to find. So s equals ut plus 1/2 at squared is still true. S, u, and a are vectors. We can put them in as vectors. We could have found displacement as a vector if we put u as 0 and a as the acceleration vector that we found here. But instead of doing that, for this particular example, it's easier to just go for the magnitude of the acceleration. So that's it. That is the last section of chapter 12. Good luck with your pure maths.